In this video, we're going to implement a linear regression example in Python, and this is just a follow-up to the video series that we've been doing in linear regression, where we started with a general video describing the concepts and are implemented in R. So we're going to just replicate the same example in Python, and we are using some dummy-generated medical data, and our aim is to predict the medical cost based on some descriptive, X variables such as age, cholesterol, and sex. So the first step that we're going to take is just go ahead and import our libraries. So the first library we are going to use pandas, numpy, and also matplotlib, and finally also seaborn just for visualization. And then so what we have, I've imported them as with their LSS, PD, NP, PLT, and so forth. And then also import our dataset, the same dataset that we're going to use. Finally, we're going to just see the first observations of the dataset, and this is what we have. The first 5 observations. We can see we have a mix of numeric and categorical variables. You can also go ahead and just see the info of the data, which will just give you the type, also the type of the dataset. We see, just as I've mentioned, we have some object data and some numeric data nature. We can also use the describe function, and the describe function will just give us the summary statistics of the numeric variables, the mean, the standard deviation, the minimum, of course the maximum, and the quartiles. And then also, just similar as what we did in R, we can just do some visualizations. And the first one that we're going to just try and see is a histogram with a density plot for the medical cost. I'm using a white grid here, white grid background, and what I'm just going to take is the fig size, 10 by 6, then take my data and place it inside the SNS east plot, and then add KDE equals to true and set the number of bins is equals to 30. So the KDE will give me the kernel density distribution on the graph. So this is what we have. And you can see that our graph is slightly skewed to the right. However, we can also see our median is around 11,000, where half of our respondents are. I can also go ahead and just have a pair plot, and a pair plot is a simple way of just seeing the correlation or just the distribution of your graph. It doesn't take long to run, depending on the data set, and also depending on the size of your memory. So we can see here the distribution along the diagonal axis will be the variable, and then also along each side you can be able to compare like age versus BMI and so forth. The other thing we're going to do is just generate a correlation matrix for the continuous variable. And what I'm doing here, I'm dropping the non-numeric variables. I created a data frame known as health numeric, which was just a copy of the original data. Then dropped the categorical variables, which are sex, region, smoker, and diabetic. So we can see these are the first 5 observations of the continuous variable. Then just use the .core function just to generate the correlation matrix. I'll go ahead and just use the heat map to visualize the correlation matrix using 2 decimal places. The annotate function is used to explain, just to annotate the heat map, and also add the Coulomb theme, so that you can just see this beautiful color that we have here. So just as a heads up, you can see the correlations between our variables. For example, exercise frequency and BMI have a correlation of negative 0.051. Also, we can see medical cost and age. You can see that it points out to an increase in age results to an increase in medical cost. The last thing that I did was just to see the distribution of across each categorical variable, how is the data distributed, and this is what we have. You can see that we have 20 individuals who are diabetic and 24 who are smokers, and then the distribution by sex is almost equal, 51 female and 49 male. The last visual that I did was just to come here and see if we have box plots distributed by across each categorical variable that we've seen, the 4 of them that we have here. And to do this, I just used a subplot. I first defined a white grid background, and then the whole fig size will be 24 by 10. And then now we'll have subplots. So for each, so 141, 142, 143, 144. And for each, I just following the same format, but I'll explain the first one, then each of them will be just changing the X component and the U. So here we take in the sns.boxplot, define our X variable as the first categorical variable, which is X, and then Y is the medical cost, and then data, our data, and then of course palette. So we want to color by each of the X variable that we have here, and I'm adding the U equals to X so that since the newer versions of Python does not allow you to just use palette without defining the U, so that you can be able to differentiate those colors properly. So I do the same thing about the title, just name the title, then the Y label, and of course the X. So what we do, all this section, we go ahead and just replicate, changing the last digit here so that it can be from 1 to 2, then of course the X variable, the X and the U, then of course next here 3, do the same, and 4, and then finally just show the graph. So this is what we'll be having, and this allows you just to visualize across, just to see what is the median amount of medical cost being paid. So we can see male have a slightly higher, then of course based on the region we see that North has a slightly higher cost, then based whether somebody is a smoker or diabetic, you see those who are either smoker or diabetic have tended to have a relatively higher medical cost. So now we get into the jigs of it, where we build the model, and the first step is going to just do the final set of the data preparation. And unlike in R, when we were able to build the linear model even without recording the data, here we need to encode the data so that we have all our variables numeric. So what you're going to do, I'm going to do it manually. So here we have set sex, male 1, then female 2, then region as defined here, and of course smoker and diabetic, if it's no, is 0, and then yes equals to 1. So I'm doing it manually here, but later in the later videos, as we get deeper into machine learning, we'll be doing it automatically using the label encoder and so forth. So here we define a function using the if else. So this is what it says. So we define a function called sex record, and it will take the variable sex, then say if sex equals to male, then return 1, else return 2, because now we only have those two. Then of course for the region, we said north is 1, south is 2, east is 3. Of course the remaining now will be west, which will just be 4. And then for yes, no, if it's yes, return 1, and no equals to 0. So this is what we do. We define our functions, then just go ahead and just take into the data now. Now that since we have the data now, what we want to do is take in each of the variables and just go ahead and apply the function so that it can replace all categorical data into numeric. And when you see the first observations, it will be having been implemented based on the functions that we highlighted earlier. So just to confirm, confirming that everything is numeric. So here we're just confirming that, and we can see that we either have int or float, which are just all of them are numeric. So we've already been able to prep our data. So now we just import the packages that we'll be requiring for linear regression. And the first one, we need to split our data into train and test split. So from this, we're going to import it from sklearn.model selection. We're going to import train test split. Then from sklearn.linear model, we're going to import linear regression in order to build the model. Then we're also going to import SM. So this one will help us now extract the p-values from our data. Then of course from SciPy, we're going to import stats. And then lastly, we're going to import metrics from sklearn, so that will help us to define our model evaluation. What I like doing is just come ahead and just list all the columns, so that as I go ahead and split, I can just copy rather than just typing where I may add a space and maybe that element is not listed as the way I've typed. So I will list all my X columns, and I'll just extract them from health data. And then since it's a list inside a list, I'll remember to have 2 square brackets, but where I'm only using one element, I'll just use, like for the Y variable, I'll just use 1 square bracket to extract it from the health data. And then we go into splitting into training and test, and we're using the function train test split, which takes in the y, the x, the y, and then of course define the test size. I'm using 30, also 70 to 30. And then I'm going to take a random state of 42. You can take any other random state like 101, like 50, but in case you want to have similar results as I've done, just use the same numbers I'm using here. Then the next thing, we just create an instance of the model linear regression, which will be setting as LM. So the model that you're going to fit will be LM. So we've created linear regression as LM. And then now we are going to say now lm.fit. What are we fitting? We're fitting x train and y train. So we'll take all the x train variables and the y train variables, which are 70% of the original data. Then next we just try to display the coefficients and the p-values. So what I'm doing here, I'm extracting the coefficient df, which will be a data frame, which will take the coefficients. We'll take the coefficients from here. So lm, the element that has been fit now, we extract the coefficients. Then of course, we take the x columns, and then the columns will be now the coefficients. So that's how we are doing it. We are creating a data frame of the coefficients extracted from this LM element. Then remember we had x columns. These are the x. We want the x, the name of the column, so that can be side by side in the data frame. Then of course we're going to add another one. Of course, at the bottom we're going to add the intercept, which will be now the intercept. So we're going to add a last row for the intercept using this function. Then of course we add the constant of the independent variables, and then we are going to extract using the SM function, the SM that we imported. Now we just want to fit and estimate and extract the p-value so that we can add into our model, our data frame. So this is what we have here. Now we have a data frame of the coefficient and of course the p-value. So this is what we have. We set the indices of each of the variable as the x column. We can see, as we try to explain, just as we did in R, we can see that age, given a unit increase in age, we see that the coefficient, what we have, that the expected medical cost increases by 50. Then we go to whether a smoker, if somebody is a smoker, we expect that compared to a person who is not a smoker, we expect the increase in medical costs by 50.72. But given a unit increase in frequency, when we keep all other factors constant, remember that how we explain this, will be keeping all other factors constant, we expect a negative 77 decrease. So we have negative 77, so the medical cost will decrease by 77. When you have a minus, it's a decrease, and so forth and so forth. Yeah, so the estimates, the intercept doesn't usually give a good explanation, because it tells us that when everything else is zero, which in ideal life does not usually happen, the medical cost is a negative cost. Lastly, we are going to do some model evaluation, and the first thing we're going to do is the predictions. So what we just do the predictions, we just use the lm.predict function, and remember we had instantiated a function of the linear regression and set it to lm. So we just going to, what are we predicting? We are predicting using x test. So these are new data that hasn't been seen, the 30% that we kept it aside. So when we run that, we can see no need for the y test. Let me just get rid of that. So those are our predictions, and you can, if you want to see, you can just list them so that you can see the observation. So this is an array, the list of our medical costs that have been predicted, 30 of them. Then you can just try and see a scatter plot between the predicted versus the actual. Remember, this is now will help you now to come and build the residuals, but you can see how do they compare. So the predicted and the actual. So you remember, it's supposed to be almost a near prediction. So we expect a linear function, a scatter plot that each observation just tells us, so that our predicted values are a real picture as the actual values. So we can also plot the residuals, which is the difference between the y test and the prediction. So that's our residuals. Y test minus predictions gives us the residuals. And remember, we want them to follow a standard normal distribution. So we just want to see how is the distribution. Can we say it's normal? Can we say it's doesn't behave so much normally? But this one really tries, although it's not a perfect normal where we see the mean at the center. but it's slightly skewed to the right. Remember, our distribution was slightly skewed to the right, and maybe that could be as a result of our class, but our residuals perform fairly well. The last set of metrics we're going to use is now the mean squared error, the R squared. And remember, the R squared tells us the percentage of a variation in the Y variable that is explained by our X variables. So what we have, we import from sklearn.metrics, we import R squared score, so that can help us compute that. And what it does, it just takes R squared, then the Y test and the prediction. So for everything, we'll just be taking like the mean metrics dot. We imported metrics from sklearn, so metrics dot mean absolute error, and then Y test and prediction, and so forth and so forth. And then finally, we create a data frame. We'll be calling metrics, and then it will list this, then create a series now using index as our metrics. And this is what we have as our output, of the metrics, where we see that our R squared value is 8.3 times 10 power negative 0.1, which just tells us that our model explains 83% of the variability in the Y variables. So the X variables have been able to explain 83%, which is a fairly good metric given the instance that we had in our dummy generated data. So there we have it, guys. We've been able to implement a linear model function in Python. We just went into the same steps that we did in R, where we just took the data, did some EDA, just generating just to get to understand the data, and then went ahead and did the final set of data preparations, where we converted all categorical data into numeric, and then finally just built the model and understood and generated the coefficients, and also went ahead and finalized by doing the metrics, seeing the predicted versus the actual, plotted the residuals, and finally just extracted the value of the R squared. So that has been the series on linear regression. The link to the previous videos can be found in the description, and also the link to the codes. The GitHub link is also in the description of the video. Thank you guys for following on this series, and I'll see you in the next one.